Hello, this is the next video in a playlist that I'm calling Introduction to Mathematical Statistics. And we're in Chapter 3, part of this playlist, which I'm calling Continuous Random Variables. And today's topic is the standard normal distribution. And in my opinion, the normal distribution is by far the most important probability distribution in statistics, hands down. The standard normal distribution definition is let X be a standard normal random variable, then the density for X is given by this. F of X, often denoted by phi of X, that's the lowercase Greek letter phi, which is this, 1 over the square root of 2 pi e to the minus x squared over 2. Notice there's no parameters in here, and that's why that's the standard part of the standard normal. There's no parameters. Now the standard normal cumulative distribution function, let X be a standard normal random variables, then the CDF for X is given by this. This is the capital Greek letter phi. So phi of X is the probability that X is less than or equal to some number little x, which is the integral from negative infinity to x of the density for the standard normal distribution. Let X be a standard normal random variable. The mean and variance of X are given by, the mean is 0 and the variance is 1. And I'm going to point you to a video I have in my playlist. I often prove these, but these are proved so much, and I've even proved them several different ways on my channel. So I'm going to point you to a video that I call Derive the Moments of a Standard Normal Distribution. And we derive these and many more. It's a nice video and worth watching. Next theorem, let X be a standard normal random variable. The moment generating function of X is given by the expected value of e to the tx is e to the t squared over 2. Here's a quick little proof. So e to the expected value of e to the tx means takes e to the tx times its density integrated over all possible values. Well, we combine the e's into this expression. Then from this exponent, we factor out a minus 1/2, and then we complete the square, and there's a constant left over. Well, we take that constant and move it out because it's not part of the x world. And then what's left over becomes what's called a normal distribution with mean t. And this integrates to 1. So that's often what you try to do, is you try to trick your integral into looking like a common probability density function. And you know it integrates to 1. And then what's left over is e to the t squared over 2. And that's what we wanted to show. Now let X be a standard normal random variable, then phi is an even function symmetric about 0. So phi is the density, the standard normal density. So, and this is a quick little proof. Phi of X is, you plug in X, and that's here, so it's X squared. But notice if we take minus X squared, that's the same thing as just X squared. But if minus X squared, that's phi of minus X. But that's the definition of an even function, which is symmetric about 0. Now, calculating probabilities, let X be a standard normal random variable, then the probability that X is between two numbers A and B is given by this expression. So the probability that X is between A and B is the integral from A to B of the standard normal density. And notice that I have forgotten dx in all of these, and so I'll fix that in the hard copy. Well, this here, instead of going from A to B, we go from minus infinity to A, but then we have to subtract that piece out. But then these are CDF functions, capital phi of B and minus capital phi of A, right? The CDF functions. And that's generally how you calculate probabilities in with this. Now with, computers, you don't have to do it this way, but when you're using the book in a class, this is exactly how you do it. So most books contain the values of a standard normal CDF. Now, before we end this video, I'm going to show you a mapping. And the reason is this. So in a later video, we're going to look at the normal distribution. Now this is the standard normal distribution. And in the books, they have the CDF for the standard normal distribution. So what we do is we map a normal distribution down into a standard normal distribution, and then we calculate probabilities, and it's the same. And I always get asked, well, how can you do that? How can you just map it down? Why are they equal? And so I want to give you a illustration, and the R code is not important. It's the picture that we're going to look at. And what this represents is the entire real number line being mapped into the interval 0 to 1. They're actually equivalent. And this is how you do that. So if you take the interval 0 to 1 and create a semicircle and put a point at the origin, and then you have the real number line, above it, then every line segment that you draw to that real number line is a point, and then you get a point on this semicircle, and those two are mapped together. And if you move this line, this line, any movement, big or small, this we get a different point around this semicircle, and so those 2 points are mapped. And it's also reversed. So if we move this line big or small, no matter how small, we get another point up here, and those 2 points are mapped. So the entire number line is mapped into the integral 0 to 1. And you can kind of see as you go out, it's further and further and further and further, and then eventually, you get infinity essentially. So, if we can map the entire real number line into the integral interval 0 to 1, then it's easily possible to map a normal distribution into a standard normal distribution, and then look the values up in the back of a book. And I'll re-illustrate that with another picture when we talk about the normal distribution. Okay, we're at 7.5 minutes. I'm gonna call it quits for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks, bye.